Chem 11, 10 students. Now we're going to finish up Chapter 8, talking about different kinds of chemical reactions, reactivity of different elements that are in the periodic table. And so we're going to look at some general trends. The chemical behavior in a group is similar because you have similar valence electron configurations. However, the first element in a group, and fluorine is the example here, often have a different reactivity, and that's generally attributed to the fact that the first element in a group, so generally it's going to be row 2 elements, are very small compared to the other members in the group, the ones below them. All right, so there's something else to keep in mind, and it has to do with that size, is that chemical reactivity of the elements often have similarities along a diagonal relationship. So in other words, lithium, beryllium, and boron. Lithium is the alkali metal that is in the first one. It's in the second row. So lithium, beryllium, and boron have atomic numbers 3, 4, and 5. They have very similar chemical characteristics to magnesium, aluminum, and silicon. So those are the next row down, but one to the right. So they're considered diagonal. And generally this has to do with size. So they have some very similar reactivity, which is shown this little example here at the bottom of this slide. All right, so we're just going to talk about some of the groups and their reactivity, but we're going to start with hydrogen. Hydrogen is a very unusual element. It's the very first element, and it is truly grouped by itself because it's different from everything else. It can form a cation by losing its electron, and it has a +1 charge then. Less common, but it does happen. It can form an anion by pairing to the electron it already has, so it would have a -1 charge. And those hydrides, when it's a -1, will react with water to form hydrogen gas and a base. So an example here is calcium hydride reacting with water. Put it in water and you get calcium hydroxide, which is a base, and then the hydrogen gas would bubble up. Okay, so now we're going to look at the reactions of some active metals. So these are generally the 1A elements. So they have an NS1 electron configuration, and we're talking where N is greater than or equal to 2. So lithium, sodium, potassium, rubidium, cesium, etc. They have a very low ionization energy because there is just one electron in a new quantum level. They are never found in nature in a pure elemental state because they are so reactive, and they react with oxygen to form metal oxides. And here is a picture of just how reactive they are: sodium, potassium, and cesium. So these are going down the group, and you can see they truly react violently with water. All right, the next one we look at is the 3A group. So these are the group under boron. They have an Ns2np1, one electron in that p orbital, with the n being equal to or greater than 2. Boron is a metalloid. It's very unusual, but everything else in that group are metals. The next one is aluminum. So aluminum forms aluminum oxide, and here's a diagram or a picture of it on the right of the slide. Very, very exothermic reaction, and in fact this is so hot that it is often used to start other reactions. If you put aluminum in an acid, it readily gives up its electrons and it'll form a 3+ ion. All the others in the group form +1 and +3 ions. Aluminum is only +3. All right, then we're going to look at group 4A. So this is the group that starts with carbon. So we have 2 electrons in p orbitals, and below that we have some metalloids, silicon and germanium, and then the rest are metals. They tend to form either +2 or +4 oxidation states. Carbon's unusual. It can even have some negative oxidation states. And then at the bottom we have tin and lead, and they react with an acid and produce H2 gas again. All right. Then we go to group 5A. This is the nitrogen group. You've got nitrogen and phosphorus and arsenic and antimony and bismuth. Nitrogen is a very reactive material. It forms a whole variety of different oxides. Phosphorus in its natural form is a P4. And the other 3 that are listed here are all crystalline. And there's just a note here that the acid that nitrogen and phosphorus make are extremely important ones, nitric and phosphoric acid. All right, then we go to group 6A, and these are all nonmetals. Well, the ones at the top, the oxygen, sulfur, and selenium. Then we get into some metalloids with thorium and polonium. You have 4 electrons in the p orbitals, so it only needs 2 more electrons to be isoelectronic with a noble gas. And so you can see that the sulfur and oxygen make a variety of molecules, and once again we see sulfuric acid. The picture on the right, nonmetal oxides added to water produce an acid, and the thing is there's an indicator here and the color changes showing you the presence of an acid. These are very important elements and highly reactive. And just a picture here, you can see this in the Smoky Mountains. This is the effect of acid rain. And so sulfur and oxygen are very reactive. You can have SO2, SO3 in the air from various chemical processes. When it rains, those combine with the water to form the sulfuric acid, and that's what's destroying trees, a lot of tombstones, and various statues. So acid rain is still an issue. And then we get into group 7A, and these are the halogens. Halogens are all diatomic. They do not exist in the elemental form in nature because they're highly reactive. They tend to form ionic salts because they pull electrons away from any metals, but they can form molecular compounds with each other, and that means they're sharing electrons there. They will react with hydrogen to form hydrogen halides. So the hydrogen will give up its electron to a halogen. And here is an example of it. You have hydrogen gas with iodine, which is purple, and it will form 2 moles of HI gas. So that's hydrogen iodide, and you can see that once again the Erlenmeyer flask there is clear because the purple, which is contributed by the iodine, the electronic structure has changed and it no longer is colored. All right, and the last group, main group, is group 8A, and these are the noble gases. These are all monatomic. They don't need to share electrons with anything to exist. They have filled valence shells, and they were always considered completely inert until in 1963 it was discovered that xenon and krypton could form some compounds, and if you look, those are towards the bottom of the noble gas group. However, there is no major industrial use for these elements. If we want to compare group 1A with group 1B, so 1B is the first elements in the transition metals. So they both groups, the 1A, the alkali metals, and then those first transition metals have a single valence electron in the s orbital, because for those transition metals they prefer a half-filled orbital. But the properties are very different, and the 1Bs are much less reactive than the 1As. The 1Bs have a very high ionization energy, and that's because they really see the electrons in, or the protons in the nucleus. You don't get very good shielding from the D electrons because they're pretty high in energy. They're pretty far out. However, those transition metals are often found in their elemental form in nature, and they're talking about coinage metals. You know, we have a lot of coins that are made out of copper and nickel and some of the other transition metals. All right, that's it for Chapter 8.